Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler and today we'll be doing Unit number 4, Lesson number 2 on more linear work. So in the last lesson we explored linear phenomenon, we proved that the slope of a line really is truly a constant, we looked at the point-slope form of a line. Today we're just going to dig in to a little bit more linear work. So let's begin by really trying to understand what makes two variables related in a linear way. All right, linear relationships. Two variables, x and y, are linearly related if the ratio of the change in one variable to the change in the other is a constant, i.e. the average rate of change is constant, right? That's what makes things linear. The average rate of change is a constant. All right, now I know that people really know that, but that's an important thing. What makes linear linear is that the average rate of change is always the same, no matter what two x values you pick. So take a look at exercise 1. Selected values for the function y equals f of x are shown in the table below. Do the values in the table support the assertion that f of x is a linear function? Justify your answer. An assertion, right? Nice little fancy word there. An assertion is a claim. It's a statement. Oh, I'm asserting that f of x is a linear function. Does this justify your answer? Well, go along and play around with it. Pause the video now. All right. Well, the plain fact is we can calculate all sorts of different slopes. So for instance, let's calculate the average rate of change here, delta y to delta x, right? Well, the change in y is 6 units, the change in x is 3 units, so the slope is 2, right? If we calculate the delta y to delta x here, all right, the change in y is 4, the change in x is 2, 2. It's looking good. How about we do it here? The change in y is 6, the change in x is 4. Uh-oh, that's 3/2. So the answer is no, absolutely not. All right? You know, in order for it to be linear, then the average rate of change between any two x values or any 2 points on the function has to be constant. And as soon as one of them isn't constant, then this is not a linear function. All right. Well, pause the video now, write down anything you need to before we look at another important idea about slope and linear functions. All right, let's take a look. Now, something like exercise 1 you've surely done before, but this critical slope fact that I want to talk about next is, well, it's critical. It's really important. Now, in my class, we've talked about this before, so students have kind of gotten to understand it a little bit. But I really want you to get something. You know, we've been calculating slope for a long time, playing around with it. But we almost always think about slope as being the change in y over the change in x. But one thing that's important is to understand that the change in y can always be calculated by taking the slope and multiplying it by the change in x, right? So the change in y is the slope times the change in x. Now, a lot of students kind of instinctively know this, especially when they think about something like, let's say we have the line y equals 5x minus 2, right? We all know that the slope here is 5. But what that means is if I told you that x increased by 3 units, what it would tell you is that the y increased by 15 units, i.e., right, the change in y is 5 times the change in x. That's what slope is. It's how many times greater the change in y is than the change in x. All right? Now, as well, we can combine that with the fact that if I know an initial y value and I know the slope and the change in x, then I can find a final y value. This should also make sense, right? This just comes from the fact that, you know, the change in y is y2 minus y1. So y2 will be y1 plus the change in y. But the change in y is just m times the change in x. So let's apply this. Exercise 2. For a particular linear function, it's known that the slope is -5 and f of 3 is 18. Now, what I'd like to try to do in this problem is avoid coming up with the equation for f of x. Could I do it? Sure, that's what we did in the last lesson. But let's try to avoid doing that. Let's try to use this idea that the change in y can always be found, let me circle it in red, the change in y can always be found by taking the slope and multiplying it by the change in x. Okay? So for instance, letter A, it says if delta x is 4, then find the corresponding delta y. Well, again, delta y will always be the slope times the change in x. The slope here is -5. If the change in x is 4, then the change in y must be -20. Now again, I really want you to understand that, right? It's not just a number. What it means is that for every 4 units that we increase x along this line, y goes down by 20 units, right? For every 4 units we go over, we go down 20 units, right? That's what that means. Now let's take a look at this. It says determine the value of f of 7. Determine the value of f of 7. Well, I claim that based on letter A and based on this, f of 7 should be very easy. Think about why that is. Pause the video now. All right, well, let's take a look why. Right? Here we've got f of 3 equals 18. Right? Then we're looking for f of 7. Well, when x goes from 3 to 7, the change in x is 4. So the change in y here needs to be -20. I'm going to have to pause the video for just a minute because my phone's ringing. All right, I'm back. Sorry about that little glitch. We were at a point, though, where we had determined that, okay, f of 3 is 18, and we're trying to figure out what f of 7. Well, the important thing is, to go from x equals 3 to x equals 7, x has to increase by 4. So by default, delta x is 4. But any time along this linear function that delta x is 4, then delta y is -20. So if I'm starting at 18, and I decrease by 20, f of 7 must be -2. So this is really this idea that we can always calculate a second y value by taking a first y value, right, that 18, and adding on to it m times delta x, right? So in this case, the y1 was 18, right? The m was -5, and the delta x was 4. And that gave me a y value of -2. This is actually quite important. Even if you're saying to yourself, look, I can come up with the equation of the line. I can figure out f of 7 from that. That's great. That's great, and it's a good skill to have. But it's also important to understand this, especially if you're planning to study BC calculus or any advanced calculus. I'm just going to get rid of this right now. All right, so what I'd like you to do is try to use the same approach to think about letter C and letter D. Letter D is a little bit trickier, but try to work on both of them, and then we'll come back and we'll go through them. All right, well, here we go. Right? We know that f of 3 is equal to 18. We're looking for f of 12. Right? What we know is that we know our delta x, if you have to do the subtraction, 12 minus 3 is equal to 9. Therefore, the change in y, which will be m times the change in x, will be -5 times 9, or -45. But that means now that f of 12 no longer has to have a question mark behind it. We can just say that's y1 plus the change in y, which ends up being -27. Now, f of 0 is a little bit of a challenge, right? But you can actually treat it quite mechanically. All right, the reason that it's more of a challenge is that you really have to be confident in what's going on here. I know f of 3 is 18, and I want f of 0. Well, here now my delta x is not 3, my delta x is -3. Therefore, my change in y, which is still m times change in x, that doesn't change, is -5 times -3, or +15. So again, we can now erase the question mark by f of 0, and we can say f of 0 is my y1 plus my change in y, which must be 33. Isn't that cool? Now, if you thought that the change in x was positive 3, then what would happen is you'd get the change in y to be negative 15, and you probably would think that f of 0 was 3. But that would be a little bit weird, right? If you got f of 0 to be 3. Just think about it graphically for a minute here. That would mean that at 0, we were at 3, and at 3, we were way up here at 18, right? But that would tell us that our line had a slope that was positive, and yet we know our slope is negative. So that can't be the case. All right, well, there's a lot that's important on this sheet. And on the next sheet, we're going to directly extend this work to do linear interpolation and linear extrapolation. So pause the video now and write down anything you need to. All right. I'm going to clear it out. All right, so the final topic that we're going to look at today is linear interpolation and linear extrapolation. Now, probably most of you have heard about these before, maybe in your science class. I got to work a lot with linear interpolation and extrapolation because I've had some experience in engineering, and we do this all the time. It's a very simple idea. It's the idea that we go out into the field and we have some set of data, x1, y1, and then some other point, x2, y2, and that's all we have. And let's say we then want to predict the y value of some x value that's in between these two. All right, some x value that's in between these two. The idea of linear interpolation is, well, okay, whether I know it's a line or I don't know it's a line, what I'm going to do is I'm going to assume it's a line. Now I lost my 2 points. I'm going to assume it's a line, and I'm going to use that linear relationship to predict a y value for that particular input. This is what's called interpolation, because the thing I'm trying to predict is inside of my first x value and my last x value. Now that might be a good prediction, or it might be a terrible prediction depending on how linear the relationship is between the two given points. On the other hand, extrapolation is the same idea, except we're going to try to predict the y value for an input that is outside of the two inputs that were given. So now I want something out here. Now, as many of you have probably learned in science classes and other classes, extrapolation is a bit dangerous, right? Extrapolating, well, you never know, right? Maybe the trend between those two data points extends for a while beyond it, but maybe it doesn't, right? Interpolation tends to be safer than extrapolation in terms of its predictive value, but they can both be good and they can both be bad. So let's jump into a couple of real-world examples of interpolation and extrapolation. Write down anything you need to right now, even though these pictures aren't actually in the worksheet. All right, I'm going to clear them out. So, exercise 3. In a chemistry experiment, it's known that the temperature of a liquid has a linear relationship with the amount of time that the reaction has been occurring. After 4 minutes, the reaction has a temperature of 34 degrees Celsius, and after 10 minutes, the reaction has a temperature of 103 degrees Celsius. Determine the temperature of the reaction after 6 minutes. Is this an example of interpolation or extrapolation? Explain. All right. Well, look, I just want to concede this right away. One thing that I could do right away is I could just form the equation of the line and use it to do all the predictions. But what I want to do is I'd like to use an approach like what we did in the last exercise. In other words, I've got this one point, which is what, 4 minutes, 34 degrees, and I've got this point at 10 minutes, 103 degrees. All right. From that, I can clearly calculate the slope, right? The change in, I guess, Celsius divided by the change in time, if you will. Is that okay? Which would be 103 minus 34 divided by 10 minus 4. And that gives me, what do I get? Nice 11.5 degrees Celsius per minute. Now that's a really nice thing to have the units there, right? Because it really gives me a sense that for every minute that goes by, my Celsius temperature increases by 11.5 degrees. Now, let's say I now want my temperature, right, at 6 minutes. Well, I can then take my temperature at 4 minutes and add to it my slope times the change in time. Change in time, right? Right? So C4 is 34 degrees Celsius plus 11.5. Watch the units. Watch how nice the units are. Degrees Celsius per minute times, well, how much does time change when we go from 4 minutes to 6 minutes? Well, times 2 minutes. I don't need the equation of a line to do this. I can just do that. And that will be 34 degrees Celsius. Look at how the units cancel. Plus 23 degrees Celsius, and that will give me 57 degrees Celsius. Now, that's an example of interpolation. I don't have enough room to really write down. Well, yes, I do, because t equals 6 minutes falls between or inside t equals 4 minutes and t equals 10 minutes. All right, so it's interpolation, right? And really, what we did is we just took this thing, looked like this. We knew at 4, we had 34. We knew at 10, we had 103. And we figured out that at 6, we had 57. Right? So this thing was inside of these two. Letter B asks us to determine the temperature of this reaction after 20 minutes. Is this an example of interpolation or extrapolation? Explain. Well, why don't you pause the video now and figure out the temperature after 20 minutes. All right, well, let's do it. Now, what's cool is you can approach this problem from 2 or 3 different standpoints. You could do this. You could say, well, I'm going to figure out what the temperature is, the Celsius temperature at 20 minutes, by taking the Celsius temperature at 4 minutes and adding to it the slope times the change in time, right? And again, the Celsius temperature at 4 minutes is 34 degrees Celsius. The slope is 11.5 degrees Celsius per minute. And the change in time as we go from 4 minutes to 20 minutes is 16 minutes. Right? We cancel that all out, add them all together, etc., and we get 218 degrees Celsius. Man, that thing's hot. All right, or you could say, well, maybe C20 is equal to C of 10 plus M times delta T. This would be the way I'd go if I had no calculator, right? Because C10 is 103 degrees Celsius plus 11.5 degrees Celsius per minute times, now again, delta T here is 10 minutes. Right? Those cancel, and that would be 103 plus 115, and again, 218 degrees Celsius. Because like all linear phenomenon, you really just need a known point and the slope to figure out any other output. Isn't that cool? Now, clearly this is extrapolation. So this is extrapolation. Because way out here is my 20. So I'm taking those 2 initial points, let me draw them in red, the one at 434 and the one at 10,103, and I'm extending the line outward to predict what's happening at 20. It's a lot less dicey to say, well, I'm going to assume that what's going on in between these two is a line. But boy, you never know. Maybe as you extend outward, it's no longer linear. Granted, this problem told me we had a linear relationship, so I guess everything's perfect and the 218 is perfect. But even if we didn't know it was a linear relationship, that interpolation would be more likely to be close to correct than the extrapolation. Although you never know. All right. So pause the video now, copy down anything you can or want to, and then we're going to go on and do one more problem. All right, clearing out the text, let's finish with one final problem. The price per gallon of gasoline is a linear function of the price per barrel of oil. When oil costs $60 per barrel, the price per gallon of gasoline is $2.25. When oil costs $90 per barrel, the price per gallon of gasoline is $3.82. If this trend is linear, predict the price of a gallon of gasoline when the oil is $100 per barrel. Is this an example of interpolation or extrapolation? All right, well, why don't you go ahead, pause the video, and work on this while the hallways of Arlington High School get pretty loud. All right, let's go through it. Well, first thing I'm going to do is I'm going to write this down as coordinate pairs. So $60 oil gets me $2.25 gas. $90 oil gets me $3.82. So this is sort of oil versus gas. Oil is my input, gas is my output. Oil price, gas price. So first thing I should do is figure out my slope, which is $3.82 minus $2.25 divided by 90 minus 60. Now I'm sure that many of you sort of figured this out, but it's ugly, okay? It's actually 0.0523 and then the 3 is repeated. Now I think you can kind of understand that though, right? What that means is that for every $1, right, for every $1 that oil goes up, gasoline goes up by, well, about 5 cents, right? So you can have that. I've found, and a lot of engineering schools will teach students to leave it like this, all right? Because now what am I looking for? Let me call it cost, C for cost. I keep using C, sorry about that. But let me figure out the cost when oil is $100 a barrel. Now you can start with the 60 or you can start with the 90. It doesn't matter at all. So I'll start with the 60. So I'll take the cost at $60 oil, and I'll add to it M times, let's say, the change in X. I'll call it the change in X, right? Now, the cost when oil was $60 a barrel is $2.25. The slope is ugly. It's $3.82 minus $2.25 divided by 90 minus 60. All right, and then I'm going to multiply that by delta X. Well, my delta X here is 40. And the beautiful thing about keeping the calculation like this is you don't have to worry about this messy 0.0523. You just simply multiply it all out, and you get $4.34. All right, and this is clearly, again, a case of extrapolation because that $100 does not fall between the 60 and the 90. So if you got 434, then pretty good. And watch for it. See what happens next time oil goes up to 100 a barrel. See if it reaches 434 at the tank. Right now, oil is hovering around, I want to say, about 80 bucks a barrel. So we're getting down there. And the price of gasoline is in the mid to low $3 range, which is exactly what you'd think. All right. Well, pause the video now, and then we will clear out the text. All right, here we go. Go on, and let's finish up. So today, I wanted you to just get more practice with linear functions and linear phenomena. You know, a lot of students can get all the way, wow, page 1 still cleared. A lot of students can get all the way through their math education at the high school level and never see that relationship, that idea that the change in the output can always be calculated by taking the slope and doing the change in the input. I just keep clearing that page for some reason. So, you know, that is an interesting phenomenon, and then it builds into the process of doing interpolation and extrapolation. Well, I had a lot of things disrupt me at the end of the lesson. But I do want to thank you for joining me for another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.